Rigid body kinetics, which is chapter 17 in Hibbeler if we're using the text, is probably one of the most challenging chapters within the entire course. And the reason is that there's a lot of new material that's introduced here, and in particular, a lot of you combine a lot of analysis. And so when you look at these particular problems, what I want to do is really just sort of emphasize this new idea of the mass moment of inertia of a body and the equations of motion. Now, the equations of motion are straightforward. They're the same ones as you had before in chapter when you talked about particle kinematics or kinetics, excuse me. However, you also have to do everything that you did in the previous chapter, which is rigid body kinetics, all of the geometry, all of the motion, and then apply that to the idea of force balances. So you introduce mass moment of inertia, define the equations of motion for any type of rigid body, and then translation, rotation, and general plane motion. In this part of the course, the big change that has occurred is that you have size and mass. And what that means is that the body has the capability of both translating and rotating. And so you're going to spend more time with problems like this, where you have to solve for both the force balance and the moment balance in order to properly describe everything. The big thing is this I sub g term. The translational components you've done before, and you're probably pretty comfortable with it. It's the rotational components that are new, and in particular this moment of inertia, which is a measure of the resistance of the body to angular acceleration. And you can see immediately that these sort of correlate to second law relationships and act in a similar way. But I sub g is not a material property. It's a geometric property. So for moment of inertia, we've defined it about some axis. So here I have arbitrary body. It's symmetric about the z-axis. And in this case, I want to define I about that z-axis. So I define all the distances with respect to I equals the integral of the mass r squared dm. And if I have a mass that's sort of in there, then I have to calculate its distance and all the rest of the term. And so I can do it as a volume, r squared rho dv, where rho is the density, and then I can bring out rho as the term. Most times in this course, I can't think of any in a number of years that we've really done very much in terms of density, where the density is constant. And I can always say that dm, the mass element, has a volume dv and a density rho, which is constant throughout the problem. You should be familiar with a few of these. And in particular, you're going to have to know long slender rod, which is just 1/12 mr squared. And these are multidimensional bodies I pulled off of Wikipedia, 1/12 hl squared. You have other ones that you should know. Memorizing these is not the purpose of the course, but you really have to be familiar with this. So this one, for example, 1/2 mr squared, where r1 is equal to 0. However, the most important thing you really got to know about moment of inertia are two relationships, the parallel axis theorem, where say you have a body that you've defined with respect to some axial point. The origin is at A, and dm is a distance defined by that red arrow. Y and z are two axes that cross over at that origin. X is moving through the origin at A and through what's eventually going to be the center of mass. So the distance to that body is given by d plus x prime, and in the I direction, and y or y prime, because they're both the same, in the j direction. And I can write this out as I equals r squared dm and d plus x prime squared plus y prime squared. Well, if I do that, I end up with I a, which is equal to x prime squared plus y prime squared plus 2d x prime dm, d squared dm. And that is my parallel axis theorem. And the big thing to recognize is this term right here is really this. which is r squared dm. This term over here is a new term, but the integral is nice because the integral of this is just m. And this term right here is d squared, and so I get this md squared. But if I do an integral about the center of mass, x prime on one side of the mass and x prime on dm on the other side of the mass are both equal, and this term goes away. If I have a really odd shape, often will not give you expect you to calculate it. Instead, we'll give you a radius of gyration. K has the units of meters, and it is the equivalent hoop of mass m that will describe the moment of inertia. And if you have a chance, you can look up the Short Brother landing gear catalog, and they'll give you moments of inertias or radius of gyrations for a number of different landing gears so that you don't have to do all of the calculations. K is equal to square root of Ig over m, and it has units of length, usually meters. The other thing that you've done at this point is look at composite bodies. These are bodies that have different components, say, for example, a slender rod and a disc. The slender rod has length L, and the disc has radius R. The center of mass of the rod is given here, and the center of mass of the disc is the geometric center. It's all pinned at some point at an end, and that's in a wall. And you will be asked often to solve for, say, the center of mass of the system, and that's just going to be mass of the rod times its x position, mass of the disc times its x position, divided by the total mass of the system. Same thing for y, and then you can say, look, that's the center of mass for the system. If you're dealing with moment of inertia about the pin, which is usually the more interesting point, you can say, well, it's 1/12 ml squared for the rod, which is pinned at one point, plus ml squared over 2, and you've already done this for a number of different cases, and so you know that it's going to be 1/3 ml squared for the rod. For the other term, you've got 1/2 mr squared plus m plus r right here plus L over 2 in this particular case, and there again another sort of distance to the point of interest, rod, disc. So I'm going, because I'm learning PowerPoint and doing some new animations, I'm going to make you look at this again. So the two translational motions. Out of this, you end up with the same sort of force expression, second law expression. Sum of forces is mass times acceleration g, and all of the terms in either the x or y coordinates. Sum of forces x, sum of forces y, sum of forces normal, sum of forces tangential is mass times acceleration of the center of mass, wherever that is, in the respective direction x, y, and t. But there's no moment because there's no angular velocity or acceleration. For rotation about a fixed point, say O, you have forces acting on the body. You have forces acting on the body, and you might have rotation, and you have a weight. And so all of these things come together, and you end up with normal and tangential accelerations with respect to some distance from the point of rotation, alpha and omega. So now you have forces normal, forces tangential, and moments about g. And often you don't care about moments about g, you want moments about the pin of rotational pin, I naught alpha. And that is going to be described here by the parallel axis theorem, which you'll notice here is ATRG, or r squared alpha, which is really just going to be T R G there, because AT, you know, is R alpha. For general plane motion, it's not possible to make any type of simplification. and you end up with the standard expressions force x, force y, and moments about g. The thing to notice is that in the previous example, you had rotational velocities and accelerations. In there, you did everything in nt. In terms of conclusions, moments of inertia, radius of gyration, parallel axis theorem, those are the most important things. Newton's second law for rigid bodies, three motions, translation, rotation, general plane motion. Again, I can't emphasize this enough. This is one of the more challenging chapters in the book, and certainly I do recommend that you spend the time to do homework and examples so that you're comfortable with the material. Once you do it a few times, you'll find you're really comfortable and understand what's happening. Thank you very much, and we'll talk again.